you, Alan. And yes, as Alan said, my name is Lily. I am a physician by training, and at Google, I've been repurposed as a product manager. So first off, I know that our AI session is actually tomorrow, so I'm going to give a little bit of a background, give some salient points to kind of frame the presentation for everyone. Whenever we talk about AI, machine learning, or deep learning, I find that these terms are used interchangeably, and a lot of people are a little confused about what they mean. For the context of this presentation, I've kind of divided these terms up. So artificial intelligence is kind of a grand project to build non-human intelligence. And one way to do that is through machine learning. And this is machines that learn to be smarter. And I'll get into that a little later. And of course, deep learning is a subset of machine learning that has been has gained a lot of popularity in the past few years. And it's interesting because deep learning is not really necessarily new. So the root of deep learning is artificial neural networks. What an ANN is just it's actually a unit, a computational unit, so a mathematical equation. And deep learning is basically a collection of simple mathematical units. We organize them in layers, and then we use them to model complex systems. Now, what's different in the past few years is that in the 80s and 90s, ANNs actually had a little bit of a heyday, but unfortunately, for most problems, the neural networks didn't work as well as sort of traditional statistical methods. And this is because if you look at the not to scale graph here, what happens is ANNs or neural networks actually work much better at larger scale of data, so bigger data size, bigger model size, and it's better at more accurately mimicking a system. And so now we have computers that are thousands more times more powerful than we had in the 80s, and data set sizes are much larger. And so now you could see that the ANNs generally perform much better than traditional methods. And in addition to being highly accurate, what's really, really interesting about neural networks is that you don't really have to program them. You can actually train them by example. And so what I mean by this is, in traditional computer vision, we write a lot of rules for the network to follow. So let's say I wanted to write a panda classifier. Then I would specify the ratio of black and white pixels and how they're arranged on the image, and that's one of the rules that my classifier would obey. Now, in deep neural networks, we actually, instead of writing these explicit rules, give thousands of examples, around 5,000 or so, of each class. So 5,000 examples of pandas, 5,000 examples of brown bears, et cetera. And the network learns the features itself. So what this does for us is that it rebalances effort invested to innovate. And what that means is, instead of spending a lot of time feature engineering, this orange portion here, we actually spend a lot of time now in data preparation, this is numerical optimization and model architecture. And we spend very little time writing these rules. So this is a really exciting technology, and where can we apply it where it has the most impact? Well, in general, it seems that these algorithms are really great where expertise is limited. And so here's a chart of the number of radiologists we have per certain population. And you could see that this is for radiologists, but there's a global global shortage of doctors everywhere. And so medicine is generally a pretty good place to apply something like this. It's also really good for problems where there's a lot of data to look through, and this data is somewhat standardized. So in screening programs, for example, it's a really great place. And then also where predictions are actionable. And what I mean by that is the imaging or the data that we have itself is used directly, those results are used directly to affect the way that we manage and treat a patient. So I'm going to go over those two examples in detail. So one of the first example is in screening, and this isn't cancer screening, but this is one of the most cost-effective screening programs. The other ones are around, cancer, and a lot of things that we learn from our experience in diabetic retinopathy really applies pretty well to cancer screening. So first off, what is diabetic retinopathy? Well, it's a complication of diabetes. So all 415 million people with diabetes are supposed to screen once a year for this disease, and it causes blindness. This is done by taking a picture with this special camera here through the pupil to the back of the eye, and you get a picture like this orange thing here. And this is doctors diagnose DR by grading the amount of little splotches, so these hemorrhages here, around the eye, because these are bleeds. And sometimes they're very small, subtle findings, and sometimes this one's pretty obvious. And we grade these images on a scale from 1 to 5, or well, from no DR to proliferative DR. And unfortunately, in many places, like in India, there's a shortage of medical expertise. So in India, where we are partnered with a couple of eye institutions there, there's a shortage of 127,000 eye doctors. And as a result, about half the patients suffer some sort of vision loss before they're diagnosed. And of course, this is 100% preventable, so this is something that should never happen. So what we did, working with Arvind Sankara and actually a US-based teleophthalmology screening provider, we trained a neural network to help interpret these images. And so to do this, we hired 54 US board-certified ophthalmologists, and our partners contributed about 130,000 images. And we had these ophthalmologists grade these images actually multiple times. Some were between 3 and 7 times because doctors' opinions tend to vary. And so we took these 880,000 diagnoses, these images, and we put them through a convolutional neural net. And this is a pretty well-known one. It's called Inception. It's used for cats and dogs. It's now been repurposed to do fundus images. And it works pretty well, as we would expect. And in fact, this is a paper that we published end of 2016, where we showed that these networks were able to classify fundus images at an accuracy that was slightly better than the median ophthalmologist. And this was actually pretty well received by the medical community. So after publishing this paper and showing that these networks are really, really accurate, one of the things that we started working on was, if you remember, I mentioned that these networks learn by examples. So we didn't write rules. And so one of the criticisms around the networks is that they're kind of black boxes. I don't like that term, but that you can't tell what the network is using to make a prediction. Well, that assumption is actually not true. It's not really true because there are a lot of techniques that you can use to get the network to show what it's using to make the prediction. So this is another example from the consumer space, where the network's asked to show me where in this picture is the most important pixels for this particular prediction. So, hang on a sec. So here is a Pomeranian, and the network's telling us that there's something around the Pomeranian's face that makes it look Pomeranian-y. And this is an Afghan hound, and here's sort of the silhouette of the Afghan hound. So we took this technique and we applied it to fundus images. And so here's an example of a fundus image with mild disease. And it's mild because I can't tell that this is diseased. But in fact, there are little microaneurysms, what we call little red dots, which are little outpouchings in the capillaries here and here. And so we trained the network, showing them lots of pictures of mild disease, lots of pictures of no disease, et cetera, et cetera. And then we applied this attention technique, and it found the microaneurysms. So up here and up here, very subtle. Here's another example. This is of moderate disease. It's a little more obvious because I can tell. There's lots of bleeding here, and there's some bleeding here. What's really interesting about this particular example is that there are actually 2 artifacts in this picture. So this thing here is a dust spot, and this is a corneal reflex. So these are all artifacts And you could tell that the networks learned to ignore them. So pretty good. So what's next? Well, we've shown that these networks are very accurate and that we could potentially generate some maps that explain what it's looking at. And of course, then the next step is to try to put this into a clinic. And in order to do that, there's a lot of things that we have to do, including clinical and regulatory, so showing that the network is safe and effective. And then also partnering with people who've done delivery of healthcare products in real life before. So our sister company, Berkeley, and Nikon Optos, they actually make these really amazing, easy to use cameras. And so one of the interesting things is that if you can't take a picture, you can't actually run the software, right? So, and these cameras aren't always easy to use. So sometimes a barrier to screening isn't, the AI or the interpretation. It's actually the healthcare delivery, and then also getting the image itself, the hardware. Okay, so so this is an example that in screening programs where deep learning can, we think, make a difference. Now, there are key considerations that I think that we should take away from this example. The first one is around the how we evaluate the model. So, for example, what is the ground truth? What are we using as a ground truth for the image? Are we using a consensus doctors? Are we using a biopsy? That actually matters a lot because the network will predict whatever label you tell it to predict. And of course, we should evaluate the training sets. How big are the training and validation sets? And how generalizable are our results? How many test or validation sets do you have? So that's how we generally look at the models themselves or evaluate the models themselves. And then the second consideration is around implementation and impact. So understanding how the models interact with the doctors is actually quite important because you can have an extremely accurate model that a doctor does not believe and you've done nothing. So, and then also how this model interacts with the healthcare system. So if you detect a lot of people with diseases and your detection rate goes up, your utilization rate also goes up, right? So now you have to treat these folks. So those actually have to come into consideration. And what you don't want is to do a lot of screening and flood the system with a lot of false positives. So here's another example that I'd like to give, and this is actually in diagnosis. So that was in screening. This is in the diagnosis of cancer. So after you had a mammogram, for example, and there's a suspicious mass, generally you'll get a biopsy. And then if that biopsy is positive, you'll get the cancer excised. And when you do, one of the things that we generally do is try to stage that cancer. So what we do is we take out these little things called lymph nodes that are next to the cancer to see if the cancer has spread. So this is called a sentinel lymph node because that's the one that's closest to the cancer. And what we do is take this tissue, we stain it, we section it, and we look at it under a microscope. And reading and finding these little metastases is actually very difficult to do. And so difficult, as a matter of fact, that there's a study that was published recently in 2012, I guess it's recent, that showed about 1 in 4 sentinel lymph node biopsies upon additional review had a change in nodal status. So that makes a big difference about how you would treat a patient. And it's not because doctors are bad doctors. It's really because there's tons of information in these slides. So one of these little slides is about 10 gigapixels, and that's about 1,000 consumer images. And doctors are tasked with looking through all of them for these suspicious cancers. And they're not given a lot of time. They're supposed to go through this pretty quickly. And so a pathologist, even with unlimited time, finds about 73% of the cancers on a slide. So 73% of the lesions they'll find. And they'll have 0 false positives per slide, which means if they see the cancer, it's probably cancer, but there are also cancers that they'll miss. What we did was we trained an algorithm that helps detect more of the cancers. And our trained model found 95% of the cancers, but had 8 false positives per slide. So as you can imagine, an ideal system would be a combination of the two, where you would have a high sensitivity, so finding a lot of cancers, but having a pathologist review and kind of rule out the ones that are actually cancer. In addition, we found that this technique that we had applied in these lymph node, breast cancer lymph nodes actually translate pretty well to other tissue types. So this is some work that we've done in prostate cancer. And so with prostate cancer, the grading is a little different. So rather than saying, is there a metastasis? Yes, no, we actually grade the severity of disease. And so this is an early example of some of the work that our group has done to show that the grading of the model's grading is basically on par with pathologists. Okay, so what's next? So again, we showed these models work really, really well. But the reality is studying how these models interact with readers, in this case, doctors, and how they boost either accuracy, confidence, and how the performance of these experts actually change with the algorithm. Clearly, this also applies. We can apply this to other tissue types, other types of imaging, and there's clearly a great need there, as there are some figures that say about 1 in 12 breast cancers may be misdiagnosed, and these numbers are actually similar in other types of cancers. So finally, a lot of the examples, the 2 examples that I've given are in disease detection and sort of recapitulating what doctors know, but maybe have difficulty applying under time constraints, if you're jet lagged, et cetera. And so this is an example of how deep learning can be used to make completely new scientific discoveries. So remember when I said these systems are really good at learning by example, so I could just give it a label, and sometimes that label is a disease diagnosis or disease category, but sometimes this can be how the outcome of the patient. So what we did is, this is with Fundus images as well, and one of the things that we discovered as we were working on diabetic retinopathy was that, so one of our junior engineers actually was learning how to do deep learning. And we said, oh, well, what are a lot of, copious amount of labels? Well, how about age, gender, smoking status? There's a lot of those labels. So why don't you go and predict those things? I imagine that age won't be that great, within like 10, 20 years. And, gender, that should be random. And she came back and she said, hey, it's not random. My networks can distinguish between, male and female retinas and smoking and not smoking retinas. And we thought, okay, this is a mistake. Go back, let's fix it, right? And she came back and it was even less random. It was even more accurate. And what we realized was that the network was actually learning these new things that we didn't know necessarily could be quantifiable in the image. So then what we did was we actually started training the algorithm to distinguish between people who've had a heart attack or who would eventually get a heart attack within 5 years, so a heart attack or a stroke in the next 5 years. And then we showed the network a lot of examples of people who did not have a heart attack or a stroke within 5 years. And the algorithm could tell with about 70% accuracy, if you showed them these 2 pictures, one with the event and one without, that 70% of the time the algorithm was right. And of course, we went and showed these pictures to doctors, and they said, this is a cruel trick. Why are you doing this to me? Right. And so this is actually quite interesting because this AUC of 0.7, and that's what it means, is roughly equivalent to some cardiovascular risk factor, risk calculators that we have right now. And if you remember, I don't know how many of you guys get screening for cardiovascular disease. Remember fasting, getting your blood drawn, being very cranky. Well, it's not because doctors wanted to torture you, but it was because we wanted to understand your cardiovascular risk so that we could then give you medications or counseling to help you, modify that risk. So this is very, very early studies, very early. But I think one of the promises is using technologies like this, we may be able to come up with new non-invasive diagnostics and actually, help you avoid that needle. And then, of course, the other part of this is, can we actually use this technology to better predict outcomes in terms of diagnostics? So remember those slides that I was, kind of telling you about, and we started grading, severity of prostate cancer. Well, grades are just proxies for progression. So when we say mild disease, it's like a single-digit, risk to recurrence or metastasis. And then we say severe, it generally means, a much higher risk of progression. So what if we can actually predict the outcomes directly and actually come up with new rubrics, new ways of staging and looking at risk with cancer? So there are many, many opportunities, I think, that we have in applying deep learning to improve both the availability and the accuracy of diagnosis. And one of the really exciting things, I think, is recently Google open sourced TensorFlow. It's a framework for machine learning. There are other frameworks out there that are open. And what's really exciting is that in this field, there's a lot of effort to make these technologies accessible to most people. So now there are examples of many people. There's an example of a high school student, for example, who was able to use TensorFlow to train algorithms for mammograms. So this has spurred a lot of research in the medical space, and hopefully it will spur a lot more. And so this is actually a really, really fantastic development for us to be able to translate these technologies truly from bench to bedside. All right.
Terrific. Let me start with a very specific question. You gave the example of pathology where the neural network could have a much higher rate of finding abnormalities, but also had false positives. And you said the ideal state would be a combination with a human touch. The humans could find, was it 70+%? So my question is, when you combine, can a human differentiate that extra 20 that the machine got from the 8 false positives? In other words, once the machine adds a bunch of new places to look at, can a human figure out which of those are false positives or not?
So the preliminary work that we've done, unpublished, super secret, is that yes, they can, right? But I think you bring up a good point, which is it's not just about training the algorithms that are actually quite accurate. It's about how they interact with the reader and the healthcare system itself. And so we're looking at that right now. We think that the assistant does help the doctors, but I think the honest truth is, for the most part, when physicians have a lot of time and can spend a lot of time going through a slide, they're actually quite both accurate and so they're both sensitive and specific. The issue is when they're rushed, and that's what happens most of the time in medicine, is that you have tons of patients waiting for you, and it's overwhelming you, and so you actually can't exhaustively search the slide, and that's when that's where the 1 in 4 kind of messes up. Yeah.
I'm interested in the tenor of your remarks relative to a term probably many in here have heard of, personalized medicine, and the notion of getting more and more specific about the disease that a person has. And then the premise of your work is large numbers. And I'm trying to figure out if these two can line up. Are we basically going down two routes, one where we have precision and the other where we use precision as in me alone, and the other where we use the law of large numbers to do sort of a first round screen? How do we put these two concepts together?
Yes, so I think what's interesting is that if you think about the work that we did with the retinal fundus image, what you're actually seeing is that the networks is actually looking at all sorts of many different rules that it's pretty much figured out different features in the image to come up with probably an individualized risk, right? So it's not, so generally in medicine we apply these very sweeping rules like age over 45 and you're female and therefore you should get screened, right? What's interesting here is the network is using that, and it's not really looking for your age or your your gender. It's actually looking through an entire image, and from that image trying to predict the outcome we care about, which is whether or not you'll have a cardiovascular event. So imagine, let's say you had genetic data, or you had some other sort of raw data from a patient, and you can actually come up with a more individualized risk score. Because if you think about screening recommendations, it's really about what your percentage risk is. So when we say you're high risk, we say your risk of a cardiovascular event is 10%, and therefore you should get screening or you should be treated. Well, if you're able to analyze data and use a network to directly predict what that percentage progression is, you can actually customize even the screening guidelines and treatment guidelines based on an individualized risk or a smaller risk group, rather than just saying everyone over 45 should get screening.
So let me just make sure I'm understanding that, because probably not everyone, including myself in the room, is a clinician. In essence, what you're saying is that genetic information, for example, could be another piece of data put in the large data set that you use, and it then enables the large data set with the deep learning that you're describing to come up with a more personalized sense of risk that can guide. It's not personalization so much of treatment as it is personalization of risk assessment. Is that a way to think of it?
Yeah. So what I'm describing is these images. So when you think about risk, there's phenotypic risk, and basically the expression of what your genes are, and then there's your genotype, which is what you're kind of born with. So you have the genotype that that predisposes you to cardiovascular disease or breast cancer or whatever. But you also have these lifestyle choices that are phenotypic over time, so like your smoking status or et cetera. And you can see that these networks is actually combining all of these things that from this raw data, which is the image in this case, and predicting something based on all of that, rather than one single point, one single descriptor about you. And so it's probably taking into account more than a doctor is taking into account.
So trying to think about the potential here, clearly when it comes to imaging and reading images, you start in diabetes, but that occurs throughout the cancer treatment continuum. Can we go deeper on the treatment side for what the potential might be?
Yeah, so I think it's trickier to work on treatments because there are a smaller number of people with metastatic disease or hard to treat disease. But the reality also is that there are a lot of patients who right now look the same to us, that we actually can't figure out how to treat differently. So, for example, I'll take an example from prostate cancer. So a long time ago, we used to think that prostate, we call Gleason 3+3, which is pretty low risk. At one point, for these classes of patients, we used to take out their prostate. And so we didn't, and we know that some of them recurred, but we weren't sure. And so we would take them out. And then what happened was we would redo we actually look at survival a little bit, and then we said, oh, 20 years later, say, oh, okay, we have to rewrite these guidelines because we don't, now, for example, we no longer take out Gleason 3-3s. We actually, watch them, right? Watchful waiting is what we call. And so there are these subset of diseases where we kind of treat them the same way. Some patients do well, some patients don't do well, and we don't quite know why. And so what deep learning potentially could do is generate better hypotheses about what risk factors or what features denote a higher risk group or a lower risk group. And so this is very common in breast cancer too. There are certain types of breast cancer where we kind of treat them the same way, but we know that they behave very differently. And so this is an opportunity to kind of get more out of the data that we're already collecting from these patients.
So last question for me before we open to the audience. Your citation for the openness of the medical profession to the data was from some comments and responses to the article. But I think we can't deny that there are sectors of the healthcare system where this is the source of income, this is employment, and replacing that function could be quite disruptive To a payer, that might be very positive. To a provider, it might not be so much. So what is the role of clinical medicine in this enterprise that you all are undertaking?
Yeah, so I think it's really interesting that the response we're getting around this work, because computer-aided detection has been around for a while, so it's not actually a new thing. The FDA kind of knows how to handle these technologies. I think what's a little bit different is that this is actually quite accurate. And more accurate than before, and so that might be why there's a little bit more of a response to this. But I think the reality is medicine is always changing, and imagine some of the tests that we, I mean, even if, actually, going back and going really basic, think about the thermometer, right? Before the thermometer, we would used to spend all this time, feeling someone's head, and he's hot-ish, but I can't tell if it's a fever. And now we have a thermometer which tells you exactly how feverish this person is. Does that mean that we no longer care about all these other clinical acumen, clinical things? Does that mean infectious disease specialists no longer have a job? Well, not really. It means that we have better tools to detect diseases. So, I mean, if you kind of went back to the diabetic retinopathy work, there's literally not, around the world, a shortage of people who can actually screen for this disease. And so the more people you find, the more people who have a disease, the more we can actually intervene and help those people. You actually see that it actually creates more work for some folks. So I think, medicine will change. And I hope it does change based on these kind of technologies. But I think of this as essentially a tool that makes medicine, or makes doctors better. Kind of makes us like a MacGyver.